All right, so our next step up the ladder here, we go from what the nucleic acids are. These guys look like to what a whole nucleotide looks like. So this is the individual piece of the DNA or RNA. So this is the whole monomer. This is the piece that we are going to start stacking together. So we don't just have the nucleic acids by themselves. We have some pieces attached. This is what lets us um, polymerize it. What lets us build a chain of these molecules. So this is a complete link in the chain. This guy by itself is not. This is really important. Like this is everything else we do is for this piece right here. This is what holds the genetic information. But uh, in terms of actually being able to build the large biomolecule, we can't do it without this stuff. So this is like the engine that drives the car, but good luck getting anywhere without any wheels. And steering would be nice too, and brakes certainly can be effective sometimes. So that's all the other stuff. So what we have is a phosphate, a sugar, which can be ribose or deoxyribose, and I'll talk about those more in a minute. And then the sugar is going to attach to the nucleic acid. So you have a nucleic acid, a sugar, and a phosphate. And so what they often call the DNA, or what they usually say DNA has or RNA is a sugar phosphate backbone, and that's because we actually have a sugar and a phosphate. We'll talk about that more in a minute. So this is the piece. Now, how does this get put together? Condensation reactions. So we'll talk more about that in a second too. All right, so before we go too much further, let's talk about these new pieces we've brought in. Okay, so we've got phosphate. There's only one kind of phosphate. It's ionized at physiological pH, so it has two OH groups and an O minus down here because it lost an H plus. Don't worry about that too much. Just recognize that this is what it's like, and then notice that it has two locations here where we can hydrogen bond. Okay, just be aware of that. Remember that. All right, so in terms of the sugar, we can have ribose, we can have deoxyribose. Now take a second and compare. We got ribose on the left, deoxyribose on the right. What's the difference? The name's a really good clue, by the way. Like, what's different between here and here? Hopefully you notice that this OH group is now just a hydrogen. So we lost an oxygen, deoxy. Right? Like use OxyClean to clean. Well, if they had deoxyclean, it would, I guess it would clean by removing oxygen instead of adding it to stuff to get it to react. So this is deoxyribose. Now this thing is, both of these are full of places that can hydrogen bond. So sugars are a type of carbohydrate. So these are actually technically carbohydrates, but they're showing up now. We'll talk more about them later. But one thing to be aware of is they can hydrogen bond all over the place, so we have to be a little bit careful. And another thing we can do with them is we can number the carbons in the chain. So we have this chain, this ring, I should say, so we should number the carbons in the ring. We have a ring with an oxygen in it. So it's a little unusual. You haven't seen something like this before, probably. But what we do is we just work our way clockwise, starting to the right of the oxygen. And we always want to number in a way where it's a continuous set. So we call this the number 1 carbon, or 1 prime, 2 prime, 3, 4, and 5. So there's 5. Hopefully that's showing up well. I don't have another color Sharpie, so I'm trying not to like Sharpie this up too bad. And we can do the same thing over here. So this is a 1. I'll try to write this one darker because it's the same for both. 1 prime, 2 prime, okay. 3 prime. Hopefully I haven't screwed up accounting yet. 1, 2, 3. 4 prime. Good. So it still only has 5 carbons. And 5 prime. But it has 1 less oxygen. And so ribose is used in the sugar phosphate backbone of RNA. So it's ribonucleic acid. So ribose is the R in RNA. Deoxyribose is used in DNA. So it's deoxyribonucleic acid. So the name tells you what's in it. So if you want to know the difference between RNA and DNA, or if you want to know what you're looking at, one thing you can do, shaky cam, is look at the backbone, see what sugar you have. So you can also, we talked about how RNA has uracil and DNA doesn't. You can look for uracil, or you can even more quickly, because maybe you don't see that base anywhere, doesn't mean it was even supposed to be there. You can also just look at the backbone and just see what sugar you have, because that's going to show up. Every single nucleotide will have this. They won't necessarily have a base that will tip you. And then, like I said, phosphate can hydrogen bond in 2 places. These can hydrogen bond in multiple. And so when we put a nucleotide together, this phosphate is going to hydrogen bond to this carbon. And that's going to get us, or not hydrogen bond. Oh man. Condensation reaction. Whew. All right, so this can perform 2 condensation reactions. This can perform a number of condensation reactions. We are going to get a condensation reaction to attach the phosphate and the sugar. So these are covalently bonded together. We are also going to covalently bond the nucleic acid into the nucleotide. And to do that bond to a backbone, well, this is something that can perform a condensation reaction as well, as long as the other thing has an OH group. So this OH group here will always be the one used to perform a condensation reaction with our base. And then this OH group right here will be the condensation reaction, the site for the condensation reaction with the phosphate. And that's to form the nucleotide. So this is going to be going to the phosphate, this is going to be going to the base. This is just to show you what phosphate looks like. So this is one of the polyatomic ions you had to memorize, but now you get to actually see the structure. Alright, so we put together a nucleotide with condensation reactions, and then we polymerize them with even more condensation reactions. I wasn't kidding when I said these are going to come up all over biomolecules. And so what we have, I have one nucleotide there. I want to attach another one. Well, this OH group right here will perform a condensation reaction with the second OH group on the phosphate, which will then go to another sugar, which has a base on it, and then this can just repeat. So this O down here can go to a phosphate, this phosphate here can go to a sugar, and so we can just build the sugar phosphate backbone. So it's sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate. It can go and go and go. It can go infinitely if needed. Now generally, DNA or RNA strands is going to have a set length, but the chemical makeup is not what decides that length. It's just the need for genetic information. So some organisms have very large sets of DNA because they're complex organisms, and also it helps provide protection against things like enzymes. So if all of your DNA, or not enzymes, viruses, if all of your DNA is vital information, you're supposed to keep things out of the nucleus, but every now and again, a sneaky virus comes in and injects its own DNA into your genetic code. And if it's all vital, that's going to screw it up. But if you have these dead zones, it's actually a way of protecting against it. And so then it doesn't hit a vital, like the insulin protein blueprint or anything like that. Anything vital to the cell, to the organism. And hopefully it hits a spot too where it just gets left alone. You don't start making new viruses. So when they analyze the human genome, they can actually find pieces of old primordial viruses that a common ancestor had a long time ago, and it's just dead space that it landed in, but it keeps showing up in offspring. So there's a few things you can do, or it can be really short, just because it's not a complex molecule or organism. I'm such a chemist, I refuse to even say the word organism. All right, but anyway, we polymerize, we build these chains. So we take a monomer, we make a polymer. How do we do it? Polymerization. How do we do that polymerization? Condensation reactions. Okay, and we just get this repeating pattern. So we get a sugar phosphate backbone. Now this piece I'm showing you right here, is this a piece of DNA or RNA? Let me ask you that. So, is this DNA or RNA? And how can you tell? Well, let's look at our sugar. That's deoxyribose. We got DNA here. This is a strand of DNA. And then how can you tell, if you're ever shown a piece, how can you tell how many nucleotides are in it? I usually just count the sugars. Every nucleotide equals one sugar, or one sugar equals one nucleotide. So some people like to count the bases, some people count the phosphates. I like to count the sugars just because they're big, they're in the middle, 1, 2. So I'm showing you 2 nucleotides here, and then I'm showing how they would connect to more from there. So just a heads up on that. And that's it. I mean, this process just gets cookie cutter stamped, repeated over and over and over again. So just like chemists, nature is incredibly lazy, and once it finds something that works, it sticks with it, and it just repeats the same process over and over and over again. The sugar phosphate backbone in our DNA is the same as in a fish or a bacteria or something like that. Like it's the same basic ingredients. It's just something new has been done with them. And that something new has to do with this piece over here and nothing to do with this backbone. And so it's just these pieces, more of them arranged differently to produce different proteins, things like that, to create a larger, more complex organism. All right, so that'll do it for this part. I'm going to make one more video in this section where I'm just going to sum up the difference between DNA and RNA, make sure that's clear. And otherwise, yeah, I wasn't kidding, right? Condensation reactions show up all over the place. And that's not going away. Every single biomolecule is going to have condensation reactions that polymerize it. They're not always going to be involving a phosphate. And in some ways, this is more complex than the other biomolecules because the monomer actually has to be assembled. Whereas in, say, an amino acid or a carbohydrate, the carbohydrate or the amino acid is the monomer. Whereas here, our nucleic acid has to have extra pieces put on to be able to polymerize it. So it's a little bit trickier. But I think you guys will get the hang of it all right. So yeah, so we'll do one more kind of sum up on the difference between DNA and RNA, how you can tell them apart, and then that'll be it.